I think good morning or good afternoon, and now in China it's good evening. So, so very nice to um, chair this session and welcome each speakers. So this session actually is the objective is to discuss the co-design of the GOSC. We mean, as we know, GOSC will provide service to science community. So the requirement from the science community is a key issue. So in this session, we invite actually seven speakers from four domains, two from physicals, so including the high energy physicals and space physicals, and one from disaster mitigation, and one from astronomy, and two from the Earth observation and Earth science. So which each speaker can share your experience on science cooperation and the big challenges for the infrastructure and what's your requirement for geoscore, or what's the big challenges do you think? So each one will have 10 minutes, and after your presentation, we will have a discussion and maybe answer questions or panel discussion. So that's also, I think we should, we'll start the first speaker. The first speaker is Rudolf Imbo. Rudolf is IT advisor to the European Synchrotron Radiation Facility Director. So he will present the Global Science Collaboration in ESFR. So please, Rudolf.
Thank you very much for this kind introduction. So it is my pleasure to present a brief overview what our community is and how the global reach of this community looks like. Next slide, please. So you see here the outline of my short presentation, 3 topics. The landscape of our research infrastructures, the common challenges we have, and a few words about projects and networks. Next slide, please. So here you have a map of the different research infrastructures. Those are the ones, so we are talking here about accelerator-based photon factories, user facilities. So you can see that they are scattered all around the world, covering the entire globe, except maybe for Africa. Africa is still an area which is empty, but there is a project also there. Next slide, please. So with the red circles, you can see all the research infrastructures which are based on what we call the low energy storage rings. So these facilities produce X-ray beams in the energy region of up to 3 to 4 giga electron volts. And the energy range determines to which extent the X-rays can penetrate matter and actually allow you to examine the matter for its structure, for the details. Next slide, please. So contrary to the low energy ones, you have the high energy storage rings. There are actually 4 facilities in the world which can be considered as high energy storage rings. You have on the left-hand side Argonne at Chicago, then on the top left the ESRF here in Grenoble, France, DESY with Petra 4 in Hamburg, and the Spring 8 facility in Japan. So these facilities generate X-rays and have electron beams which are in the energy range of 6 to 8 giga electron volts and can produce hard X-rays such that the X-rays penetrate much more the matter you want to investigate. Next slide, please. And then there are the free electron lasers, very large facilities, linear accelerators where the beam is pulsed and generates extremely intense lights and flashes, which again are used to probe condensed matter. Very often, unfortunately, with these extremely intense beams, the sample itself is destroyed. So you look at it while it's actually exploding. So it's a quite interesting concept. Next slide, please. And then you have the neutron facilities with whom we work together. Photons and neutrons are very often considered together. So here you have the five major facilities in the world, but the three pictures, the spallation neutron source in the United States, the ILL reactor here in Grenoble, France, and under construction, the new spallation source in Sweden, Lund. Next slide, please. Now, what are we actually doing? So we are considering ourselves as user facilities. We have every year thousands of scientists coming to our facilities with their samples. They stay for a short amount of time, typically 3 days up to 7 days in function of the research they want to do. And then they go home usually with terabytes, not yet petabytes, but soon petabytes of data, trying to analyze the data and then writing a publication. So there are thousands of publications generated from work stemming of the photon and neutron research infrastructures. And these facilities overall, we generate many, many petabytes of data every year. And the data volume is very rapidly increasing, causing a lot of headache. Next slide, please. Just one example to highlight what we are doing. One of the, let's say, more prominent examples is nanoscience. You would like to know how matter is structured. You could look at living material as you can look at anorganic material. And here on the right-hand side, you see monocrystals of germanium crystallizing on a substrate. And you can see you have this little bar there, which highlights the size, 3 micrometers. So that's 3,000ths of a millimeter. So it's really extremely small. And our photon beams, which are nano-sized photon beams, scan across these nanocrystals to see whether there are defects in the crystal structure. Next slide, please. And when looking, and here you have in the right-hand upper corner, you have the view of how that looks like. You can then judge the quality of these crystals, which are very important for a number of applications. The most prominent one being the light bulbs we have based on LEDs, but also the germanium detectors we are using in our facilities to actually do all the research we are doing. So this is typically an example which is applied in the research, but we have thousands of different applications ranging from cultural heritage to biology to material science like that. So that was just one example to highlight what we can do with high energy X-ray beams. Next slide, please. Now, data is becoming more and more complex. It's not easy for our scientists visiting us to understand what the data really is coming out of the experiments. So we have to help them usually. The data sets are in the terabyte regime these days, and they are constantly growing and quickly growing. So that means that the data analysis can really claim that we have fully implemented fair data management, but we are making good progress and we are having a consensus in all these facilities to do it in a organized manner together and profit from best practices and experience as we go along. Next slide, please. Now, coming to how we are organized, the research in the infrastructures are organized. Here in Europe, we have 2 leagues, one for the accelerator-based photon sources, another one for the neutron sources, so LEAPS and LENS. So these clubs come together and discuss their priorities. They define work programs, interact with the Commission for funding opportunities, and overall try to do things in a way that not every research infrastructure has to redevelop the wheel. So that's extremely useful and has a lot of potential in the future. So these things have kicked off a couple of years ago and are now really gearing up and starting to create let's say, added value through the activities we have there. Next slide, please. And then we have the European projects connecting to the European Open Science Cloud. Now here you have the European photon and neutron facilities who participate in the PANOSC and EXPANSE project, highlighted here with the circles in different colors. So most of the research infrastructures are together in these two projects. And so these two projects are among the science cluster projects. Next slide, please. Which you can see here on this slide, which have overall all the same ambition to connect to the European Open Science Cloud, and come with the data and our user communities to make the Science Cloud a reality and foster open science. Next slide, please. So there are other collaborations. Here you have the three-way meeting, which means a three-way